Okay, so here's a simple problem involving Amdahl's law. So there is a CPU that spends 90% of its time executing a specific type of calculation, and when running an asteroid simulation, its manufacturer makes a change that improves its performance on that calculation 15 times. All right, so 90% of the time is spent in doing that calculation and applying a certain optimization. The speed of that calculation improves 15 times. So what you want to know is what the overall speed up is, all right, of the code. Remember the example that I mentioned of about optimizing only a part of an entire process. So for instance, if I want to go from the campus all the way to California at LAX, then I would have to go from the campus to JFK and then from JFK to LAX, right? So if I optimize only the part of my journey from the campus to all the way to JFK, then because it's only a small part of the overall journey, no matter how much I optimize it, it's not going to optimize the overall uh, time of travel from the campus all the way to California. So the Amdahl's law gives us a quantification of how to measure the overall speed up. All right. So let's first consider the time it takes to execute uh, the um, uh, the operation under the old CPU. Now let t be the time to execute the the program under the old CPU. Okay. Now we know by the data given that 90% of the time is taken up in performing that whatever that specific type of calculation is, and the remaining 10% is spent by doing other housekeeping duties or whatever that might involve. Okay, and now it would, so this is, let's call this t um, right, so that's t, and now t new, this is the new time. It happens to be the same equation as the one on top, except this guy is divided by 15. All right, so our equation becomes 1 over 15 times 90 by 100 t. This is the time taken after optimizing the calculation. And since the other part of the calculation is not optimized, the time taken to execute that remains 10t over 100. And thus, the speed up is always given by t by t new, which is equal to, now the original t is just the t, all right. It is just this quantity, and as you can see, that quantity turns out to be just t in all, and t new happens to be 1 over 15 times 0.9 times t plus zero point 0.1 times t. Now we can remove t, or cancel t rather, and we are left with 0.9 over 15 plus 0.1. And let's just check what the overall speed up comes to. It comes to, my calculator tells me, it is 0.9 by 15. Yeah, and the answer comes to 6.25. So this is the the actual overall speed up. So so in general, now here I did not use the statement of Amdahl's law per se, because actually I was deriving Amdahl's law as I solved the problem. So Amdahl's law basically says that if a fraction p of your program, just like 90% of the calculation was being done here, is speeded up by a factor of s, then what is the overall speed up? So that turns out to be t divided by p times t, that is the fraction of the time taken by the part that is being optimized, divided by s plus 1 minus p times t. This is the part being occupied, this is the part being part of the calculation which is not being optimized, so it just remains at 1 minus p times t. And the overall speed up ends up being 1 over p over s plus 1 minus p. So you could have used Amdahl's law directly, but I prefer to directly use the formula and just derive the entire expression um, as I'm working out the problem. But in any case, it always helps to um, know a little bit about this. Here's a curious fact about Amdahl's law. Suppose s, that is the factor by which we are speeding up a fraction p of the program, goes to infinity, then the overall speed up does not go to infinity. In fact, by the simple application of limits, the overall speed up approaches 1 over 1 minus p. Okay. Okay, so here's a slightly more complicated example of applying the logic behind Amdahl's law. So there is an old CPU in which memory operations currently take up 30% of its execution time. All right. Scientists find that adding a cache memory speeds up 80% of its operations by a factor of 6. All right. Adding a second level of cache speeds up half of the remaining 20% by a factor of 3. By how much does the overall speed increase using these optimizations? Okay, so let's first look at the so let t be the time taken by the CPU before optimization So now we know that t is equal to 30% of t. This is the memory operation time, and 70% of t, which is the other operations. Okay. Now, scientists find that adding a cache memory improves 80% of memory operations by a factor of 6. Okay, so that means we have to consider first the division of the memory operations itself. So let's look at that. So that's 80% of the 30% of t. This is the what is that again? So this is the target for the first optimization. Notice I've not yet added in that speed up factor because I'm just considering how t itself is divided. All right, and then well, there's 80% of the 30% of t, so what's remaining is the 20% of the 30% of t, and then of course there's the 70% guy who's hanging out on the side as always. Okay, now in fact the second target for the optimization is hidden within this. So in fact I'm going to split this up even further and say this is 80% of the 30% of t plus the 10%. Remember, half of 20% is 10%, right? So 10% of the 30% of t plus 10% of the 30% of t plus the 70% of t. Okay, and now what we know is this is the target for the second optimization, and this is of course as always the target for the first optimization. So this is our important master equation that we need to look at. And now what we're going to do is we're going to go about subdividing it by the appropriate speed factors. So let's see. So for the first optimization, it improves everything by a factor of 6, and in the second case it speeds up the second optimization speeds everything up by a factor of 3, which means we can write the new time as 80% of the 30% of t times 1/6 plus 10% of the 30% of t by a factor of 3 plus the 10% of the 30% of t. Now this is by a factor of 1 because it's not speeded up, and of course 70 by 100 continues to be as it is. So let's write this in slightly less clunky form. This is 0.8 times 0.3 by 6 plus 0.1 times 0.3 by 3. Well, I forgot to add a t here. So there's a t here and then there's a t here. Times 0.1 times 0.3 times t plus 0.7 times t. That's t new. All right, and thus factoring out t and calculating t divided by t new. Remember, the speed up is always old by new, right? This is equal to 1 over 0.8 times 0.3 by 6 plus 0.1 times 0.3 by 3 plus 0.1 times 0.3 plus 0.7. Now this is just this is something that you can enter into a computer. Let's just work this out live. So this is 0.3 plus 0.7, and Google tells me that the value comes to 1.219 something. All right, so this is the speed up by applying those two optimizations.